Next we have miscellaneous examples on complex numbers. In this first one, we have to find the complex conjugate of this complex number. So let's see the solution. So in the solution, we first simplify the number. This involves many steps. So the original number is this 3 minus 2i times 2 plus 3i divided by 1 plus 2i times 2 minus I. So we straight away do the multiplications first. 3 times 2 is 6 plus 3 times 3i is 9i minus 2i times 2 is minus 4i and minus 2i times 3i is minus 6i square. Similarly, we also multiply the denominator. 1 times 2 minus I is 2 minus I. Because we have 1 here, so this is a little simpler. And then 2i times 2 is 4i and 2i times minus I is minus 2i square. So you know that I square is minus 1. So this minus 6i square becomes plus 6. 6 plus 6 is 12. And 9 minus 4i is 5i. Here also similarly 2 plus 2, because this will become plus 2, 2 plus 2 is 4 and 4i minus I is 3i. So we simplified to some extent the original number, but we still have a non-real complex number in the denominator. So we have to make it real, and that's why we multiply and divide by the complex conjugate of this denominator, which is 4 minus 3i. And then we go through a similar calculation. So here also we do the multiplication. 12 times 4 is 48 minus 36i plus 20i minus 15i square. And the denominator is easier to calculate because a square minus b square. So 4 square minus 3i whole square, so 3 square I square. So here minus 15i square would be plus 15, it is plus 15, and so that plus 48 is 63, and here minus 36i plus 20i is minus 69. And what do you get here? 16 plus 9 is 25. And then when you express this in the form a plus ib, it looks like this. So this given number actually is this complex number. So now you can find its conjugate by simply changing. What do you have to do to find the conjugate of a complex number? You change the sign of the imaginary part. The imaginary part in this case is minus 16 divided by 25. So in its place you write 16 divided by 25 and you will get the conjugate. So this is the conjugate, 63 over 25 plus 16 over 25i. Okay, fine. So actually this is the solution, but there is an alternative way of doing this also. Let's just see a little bit about that alternative. In the alternative method, we straight away write the conjugate itself like this. The required conjugate is this. You already know that the conjugate of a complex number z is denoted by z bar. So we have used that bar notation. And then you recall one property of complex conjugates, that the complex conjugate of z1 divided by z2 is z1 bar divided by z2 bar. You can distribute complex conjugate over the individual parts of a ratio. So that way we have bar over the numerator and bar over the denominator. And then we can further distribute the bar over this product and this product, because the complex conjugate of z1 z2 is equal to z1 bar z2 bar, that other property. So that way we have this, and then you can just take the conjugates of this individual complex numbers. 3 minus 2i has the conjugate 3 plus 2i. 2 plus 3i would become 2 minus 3i. 1 plus 2i would become 1 minus 2i, and 2 minus I would become 2 plus I. So this is the complex conjugate. But the problem is that this method doesn't really give you any distinct advantage over the original one. That is because it is customary to express the answer whatever you are getting in the form a plus ib. So you actually have to again go through a similar calculation that you did in the previous method when you simplified the complex number. So now you have got the answer but not in its original a plus ib form. So that's why this I won't say that you have to follow this. I mean, if you want, you can do this and then do the simplification, or you can do the original one. It's up to you. Okay, this is also a legitimate procedure. Sometimes, if you use those properties of complex conjugate, things can be simplified. Not exactly in this case, but in some places, things will be simplified. Let us see the next example. The next example asks us to find the moduli and arguments of these two complex numbers. The first one is 1 plus I divided by 1 minus I, and the second one is 1 divided by 1 plus I. Actually, in the text it's written modulus. Obviously there are two complex numbers, so it will be plural. And then even if you had one complex number, it does not make sense to simply ask us to find the argument, because a complex number has infinitely many arguments, but it has one principal argument. So if you simply are asking for the argument, means what? It doesn't make sense. So that's why I have written arguments of these complex numbers. So let's solve this. So like the previous example, here also we first simplify the complex number by multiplying and dividing by the conjugate of the denominator. The denominator is 1 minus I, its complex conjugate is 1 plus I. So we multiply and divide by that. So the numerator becomes 1 plus I whole square, and then when you expand the square, what do you get? 1 square is 1 plus 2 times 1 times I is 2I plus I square. And the denominator would fall in the formula a square minus b square. So that way we have this. Now I square is minus 1, which will cancel this 1, and we will have 2I. And again I square is minus 1, so the denominator is 1 plus 1, that is 2. Oh, I wrote I here. What a mistake. You see, this is how mistakes usually crop in. I was thinking of 2, but I wrote I. So, and this, let me just stop here for a moment. This shows why we should check. Recheck means, say you are writing an exam and you answered a significant part of the question paper, and then you actually may not get time to check whatever you did for correctness at the end of the exam. So it's better to check, say, 2 or 3 solutions that you have already done and then go for the other things. But anyway, then what are we getting here? After cancelling 2, we are getting I, which if you write in the a plus ib form, it will be 0 plus 1I. 1 I haven't written. And so what is the modulus of this complex number? If the complex number is a plus bi, the formula for the modulus is square root of a square plus b square. In this case, a is 0, which is the real part, and b is 1, which is the imaginary part. So the modulus is 1. And then we go for the arguments. If theta is an argument, there are many arguments, but if one of them is theta, then we know how modulus, argument, real part and imaginary part are related. If r is your modulus and theta is the argument, then r cos theta is equal to the real part. In this case, r is 1. So 1 cos theta is the real part, that means 0. And r sin theta is the imaginary part. So that means in this case sin theta is equal to 1. So now from these two equations, how will you find theta? For this you have to go back and see how we solved trigonometric equations. So let's see what comes out of this. So from these two equations, the values of theta that you find are these. All the odd multiples of pi divided by 2. 2n plus 1 times pi over 2, where n is any integer. N is coming from the set of integers. These are precisely the points where cos theta becomes 0. But at these points, sin theta also becomes 1. Actually in the text only this value is given, pi divided by 2, which is the principal argument. However, nowhere in the examples, in the question, is it asked that we have to find the principal argument. Simply argument is written. And you get the principal argument by putting n equal to 0 here in this general formula. Recall that the principal argument is that value of theta which lies in this interval, which is greater than minus pi and less than or equal to pi. That is why open on this side and closed on this side. Let's now see the second one. The second one was 1 divided by 1 plus I. So here also we go through a similar process. We multiply and divide by the complex conjugate of the denominator, which is 1 minus I. So the numerator simply becomes 1 minus I and the denominator gradually becomes 2. And then you express it in the form a plus bi. So in this case the real part a is 1 divided by 2 and the imaginary part b is minus 1 divided by 2. So the modulus is this. Now from this from this expression under the radical sign, you can take 1 divided by 2 outside. Actually first square will go outside and then it will get cancelled with the square root, leaving us with 1 divided by 2. Note also that this minus will vanish because we have square, and inside we will have square root of 1 plus 1, which is how we are having root 2 here. And then after a little more simplification, you get 1 divided by square root of 2. So that is the modulus. And next we go for arguments. So if theta is one argument of the given complex number, again as before, modulus times cos theta is the real part. The modulus is this, so 1 divided by root 2 times cos theta is the real part. And again modulus times sin theta is the imaginary part, which is minus 1 divided by 2. So after you cancel 1 over root 2 from both sides, you are left with 1 over root 2 on the right hand side of the first equation and minus 1 over root 2 on the right hand side of the second equation. And then from these two equations we have to find theta. So from the above equations, that means from these two equations, we see that one value of theta is minus pi divided by 4. How did we find this value? Let us recall what we did when we solved trigonometric equations. What did we do in similar situations? We first noticed where the point can lie. Where the point can lie means in which quadrant the terminal ray of theta would lie, depending on the signs of cos theta and sin theta. You know that if you consider a point on the unit circle whose center is coinciding with the origin, then the x coordinate of that point is cos theta and y coordinate is sin theta. Okay, and you know what theta is in this context. So this is the x coordinate and x coordinate is positive. X coordinate is positive means the point will lie to the right of the y axis, and y coordinate, which is sin theta, is negative. So the point will lie below the x axis. That means the terminal ray of the angle should lie in the fourth quadrant. And at the same time, we also know that when theta is pi divided by 4, both cos theta and sin theta are equal to 1 divided by root 2. Okay, so that is our Q. And that from that we guess that this angle may work. And yes, it really works. Why? Because cosine of minus pi divided by 4 is equal to cosine of pi divided by 4 because cosine is an even function. That is cos minus theta is equal to cos theta. And cos pi over 4 is this 1 over root 2. But sine is an odd function. Sine of minus pi over 4 is minus sine pi over 4. So that way we get this. So this is one argument, and in general all the other arguments will be obtained by rotating by integer multiples of 2 pi. So that's why 2n pi minus pi over 4 where n is an integer. And actually this is the principal argument because it lies between minus pi and pi. It is greater than minus pi over 4, and of course it is less than or equal to pi. Let us see another one. This example is a little theoretical. Here we don't have to consider any concrete complex number, but rather we have to prove something. It is given that the complex number x plus iy is of this form, a plus ib divided by a minus ib. Then we have to prove that x square plus y square is equal to 1. When I saw how this is solved in the text, I was astonished how stupidly complicated the text made the solution. Actually, it's quite easy and you can do it in 2 or 3 lines. Let me first tell you what the text did. The text first multiplied and divided by the complex conjugate of the denominator, which is a plus ib. So that way they get a plus ib whole square in the numerator and a minus ib times a plus ib in the denominator. And then they went through the entire calculation with this general a and b and everything. And then eventually they expressed this expression in the form real part plus I times imaginary part. Something came, okay. And then they took the conjugate on both sides, thereby obtaining x minus iy on the left hand side and something on the right hand side. And then they multiplied x plus iy with x minus iy, and that's how they got this. But we don't have to go through such calculations. Let's see how it can be solved in a much simpler way. So we start the solution, of course, with what is given, x plus iy equals a plus ib divided by a minus ib. And let us name this equation 1. Then we straight away go for x minus iy, which is the conjugate of x plus iy. So x plus iy bar, and then in place of x plus iy we write this ratio. And then we recall that thing which we used in that alternative method, that the complex conjugate of z1 divided by z2 is complex conjugate of z1, that is z1 bar divided by z2 bar. So that's how we have conjugate over the numerator as well as the denominator. Then a plus ib turns into a minus ib and a minus ib turns into a plus ib. You can probably guess what we are going to do next. We will multiply equations 1 and 2. So that way we will have x plus iy times x minus iy on the left hand side, which will be x square plus y square. And what is the right hand side? This times this. A minus ib and a minus ib cancel each other, and a plus ib and a plus ib cancel each other. So that way you have 1 on the right hand side. No need to go through the process of expressing this right hand side into the standard form and then taking conjugate. Why go through such a complex process when we have that property, when it's already given in the text? That I don't understand. But anyway, let's just do this. Okay, so we just have this. Multiplying 1 and 2, we get this on the left hand side and this times this on the right hand side. This will first, actually there is one more step here which I did not write. This will first become x square minus I square y square, a square minus b square formula. Minus I square y square would become plus y square. So that's how we have this. And here, as we said just now, we are going to get 1. So that's how you can get it quite easily. And there are some other miscellaneous examples also that we will see next week on the same day. So see you next week with those things. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.